What's going on, everybody? Back for another video. This video we're going to talk about differential equations and linear models. Got several things to go over in this one, so let's go ahead and get started. So the first thing, growth and decay. It says the initial value problem, dx dt equals k times x, where x of t naught is equal to x naught. K is a constant of proportionality, serves as a model for diverse phenomena involving either growth or decay. So as far as talking about the growth and decay, if K, the thing you want to look at, we'll talk about it in this example. All right. So let's look at this example, and then we'll talk a little more about that constant K. It says a culture initially has P naught number of bacteria. At T equals 1 hour, the number of bacteria is measured to be 3/2 times P naught. So I guess you could look at 1.5 times the initial amount. If the rate of growth is proportional to the number of bacteria P of t present at time t, determine the time necessary for the number of bacteria to triple. All right, so we have our dx dt equals k times x. We'll use different letters, but it's going to be the same principle. So we've got dp dt. Okay, so they're using p of t up here, so that's what we'll use of p, and that is equal to k times p. All right, and also we know that p of 0 is equal to p naught, because it says the culture initially has P naught number of bacteria. So at time t equals 0, we have P naught. And then it also tells us after 1 hour, we have 3.5 P naught. So that tells us that P of 1 is equal to 3/2 times P naught. All right, so basically what we have here is we just have a differential equation to solve. So we can write this as dp dt minus k times p equals 0. I just moved the k times p to the other side of the equal sign. And so here we can solve this. This is we can find the integrating factor. So if we find the integrating factor, well, that's going to be e to the what? E to the integral negative k dt, which is e to the negative kt. All right. So we're going to multiply this e to the negative kt, times each term. I'll work it all out on this example. I mean, you've solved these before, but I'll work it all out on this example just so you can see, but I won't show all these steps as we go. So if you remember, the left-hand side becomes what? The derivative of the integrating factor and p. All right. And so now if we integrate both sides, so that's going to give us e to the negative kt times p is equal to c. When we integrate 0, we get c. And so then we're gonna, let me see how much room I got. Oh, I'm starting to run out of room. All right, so we're gonna get p is equal to, if we divide both sides by e to the negative kt, that's gonna give us c e to the kt. All right, Now, when you look at this, the thing I want to mention here is this K here, this K. If K is positive, that represents a growth, and if it's negative, it's going to represent a decay. Okay, and so we can find out what C is, because we know that P of 0, which is C e to the K times 0, is equal to P naught. So this tells us that C is equal to P naught. All right, so that's going to give us P of T is equal to P naught e to the negative KT. Okay, that's what we have so far. And I'm running out of room there. All right, so we get P of T is P naught e to the negative KT. I get that. Now, the thing that we've got to find here is we have to figure out when is determine the time necessary for the number of bacteria to triple. All right, so the thing that we've got to find here is this K. We've got to figure out what K is. Well, do they give us any other information? Well, they tell us that P of 1 is equal to 3/2 P naught. So I've got P of 1 is equal to P naught e to the negative K. I'm plugging in the 1 for T, so that's just going to give me negative K, is equal to 3/2 P naught. Okay. All right. So, oops, that's not a negative up there. That should be a positive. I know. I see that I messed up. I wrote a negative. I don't know why. I must have looked at this thing right here. All right. So now this is going to give me e to the K is equal to 3/2. The P naughts, they'll cancel. And so now I'm going to take the natural log of both sides. And so that's going to give me e to the K. No, that's going to give me K is equal to natural log of 3/2. Okay, so there's that. And if I plug that into my calculator, natural log of 3/2, that gives me 0.4055. So I have P of T is equal to P naught e to the 0.4055 T. There's my function. All right. Now, I want to know, determine the time necessary for the amount of bacteria to triple. So I want to know, when is P naught e to the 0.4055 T, when will that triple? So that means when it's 3 times the amount, 3 times the initial amount, so 3 times the initial amount. So this is going to give me e to the 0.4055 T is equal to 3. The P naughts will cancel. And so I'm going to take the natural log of both sides. And so this is going to give me e to the 0.4055 T. I'm sorry, 0.4055 T is equal to natural log 3. So T is equal to natural log 3 over 0.4055 T. And so, you can leave your answer like that. That would be just leaving it in an exact form, or you could say, if you plugged it in your calculator, 2.71. I think it's in hours. Yep, hours. T equaled 1 hour. And so there you have it. So that's not too bad. You should have seen most of this stuff before. The only thing that would be new here is solving differential equation there. Okay, but I mean, you have solved those equations before in previous lectures. All right, so let's talk about half-life. Half-life is the time it takes for one half-life of the atoms in an initial amount A0 to disintegrate or transmute into the atoms of another element. The longer the half-life of a substance, the more stable it is. All right, so let's look at this. It says a breeder reactor converts relatively stable uranium-238 into the isotope plutonium-239. After 15 years, it is determined that 0.0433% of the initial amount A0 of plutonium has disintegrated. Find the half-life of this isotope if the rate of disintegration is proportional to the amount remaining. All right. So we've got dA dt is equal to K times A, where A of 0 is A0. That's the initial amount at time t equals 0. A of 0 equals A0. All right, so I'm not going to go through and solve this equation, but if we go through and solve it, we would get A of t is equal to A0 e to the kt. Okay, just like we did in the previous problem. Okay, just like we did in the previous problem. So let's see, what are they wanting to know? They're wanting to know the half-life, but let's see. We got to figure out what K is to get all that. It says a breeder reactor converts that into isotope plutonium. After 15 years, it is determined that 0.043% of the initial amount A0 of plutonium is disintegrated. All right. So if we take the 100% minus the 0.043%, that is going to equal 99.957% remains. Okay, after 15 years, that's how much remains. Okay, so we can say that A of 15 after 15 years, so we plug the 15 in for t, that is going to equal A0 e to the 15k. I'm plugging 15 in for t. How much do we have? Well, that's going to equal 0.99957 times A0. This is how much is remaining. Okay, that's how much is remaining. We're not going to set it equal to how much disintegrated. We're going to set it equal to how much is remaining. And so now we've got A0 e to the 15k is equal to 0.99957 A0. So e to the 15k is equal to 0.99957. The A0s cancel out. And so we take the natural log of both sides. E to the 15k equals natural log 0.9957. And so 15k is equal to natural log 0.9957. So k is equal to, we're going to divide both sides by 15, and that's going to give us negative 0.0002867. That's how much room. Okay, I'm starting to run out of room, but we'll be all right. So that tells me that A of t is equal to e to the negative 0.00002867 t. Okay, so yeah, I found k. Okay, now what do they want to know? They want to know what is the half-life. Okay, what's the half-life? Oops. A of t equals a naught. Okay, gotta put that initial amount in there. All right, so we want to know, when does a naught e to the negative 0.00002867 t, when is half of it left? So that's when does it equal 1/2 a naught. And notice in the problems here, it doesn't really matter if we know the exact initial amount or not. Okay, and so now we just solve for t. We get e to the negative 0.00002867 t is equal to 1/2. The a naughts cancel out. And so we've got natural log e to the negative 0.12342867 t equals natural log 1/2. And so that's going to give me negative 0.12342867 t equals natural log of 1/2. And so I'm going to divide both sides by that number there, and that is going to give me 24176.74 years. So 24,176 years. That would be the half-life. Okay. All right. Now let's look at this one. It says a fossilized bone is found to contain 0.1% of its original amount of C14. Determine the age of the fossil. All right, so okay, we can set up the differential equation. You know, you got dA dt equals k times a. And so once you solve that, well, what are you going to get? You're going to get a of t equals equals a naught e to the kt. All right, so there we have it. So remember, we need to figure out what k is, and this right here, just a little note, half-life of C14 is 5,730 years. Okay. Okay, so there's some things out there that says there was a Libby's calculated value of half-life for C14 was approximately 5,600 years. But today, the commonly accepted value for the half-life of C14 is the Cambridge half-life, that is close to 5,730 years. Okay, so I don't know, your teacher might tell you to use a different number. I don't know if they do. Still work the same. Okay, so we know after 5,730 years, when t is 5,730, that we're going to have half the initial amount. Okay, so a of 5,730 is equal to a naught e to the 5,730 k is equal to half of the initial amount. Okay, and so once again, same old thing, e to the 5730 k equals 1/2. We're going to take the natural log of both sides, just like we did in the previous two problems, and when we do that, we're going to end up with k is equal to negative 0.0001209.7. Okay, so there's k. So that's going to give us a of t is equal to a naught e to the negative 0.1231209.7 t. So there's our function there. So what does it say here? They want to know how old is the fossil. So we're looking for t. So it says a fossilized bone is found to contain this percent of its original amount, which would be 0.001. That's how much is remaining, this percent of the original amount. Okay, so we want to know when does A naught e to the negative 0.31209 t, when does that equal 0.000 A naught 1? When is it 0.1% of the original amount? And so, of course, once again, those cancel out. E to the negative 0.231209 t is 0.0001. And, of course, we've got natural log of both sides. 2097 t is natural log 0.0001. And so, of course, that's this. We're going to get t is equal to natural log of 0.0001 over negative 0.1231297. See, when you take the natural log, that goes away. You're left with that. Divide both sides. And so that's going to be 57,103 years. And that's how old the fossil would be. Okay. All right. So let's move right along. Newton's empirical law of cooling, warming of an object is given by the linear first order differential equation. D of capital T dt is equal to K times capital T minus capital T sub m, where K is a constant of proportionality. T of T is the temperature of the object for little t greater than 0, and T sub m is the ambient temperature, that is, the temperature of the medium around the object. Okay? All right, so let's use that to work this next problem. It says when a cake is removed from an oven, its temperature is measured at 300 degrees Fahrenheit. 3 minutes later, its temperature is 200 degrees Fahrenheit. How long will it take for the cake to cool off to a room temperature of 100 degrees Fahrenheit? All right, so here, let's see, what all do we have here? Okay, so when I wrote this up, I left off that room temperature is 70 degrees Fahrenheit. Okay, we need that little bit of information. All right, so let's go ahead and work this problem. All right, so we have, oops, let me change colors. We've got dt is equal to K times T minus T sub m. And we know here that T sub m is 70. So we got dt is equal to K times T minus 70. All right. So, well, what do we have here? We have a differential equation to solve. And, well, how would we want to go about solving this? Well, I think we can do this as 1 over t minus 70, okay, times dt is equal to K dt. It's a separable equation, right? And so this is going to be what? The natural log of t minus 70 equals, we're integrating both sides, k plus what? kt plus, we'll call it C1. I don't know, we may want to rewrite the constant. I don't know, we'll see. Okay, we may need to rewrite the constant here. And so what I'm going to do here is, let me see how much room I got. Oh, I'm already about to run out of room on it. All right, so if we raise both sides to the e power, that's going to give me t minus 70 equals, and this e to the kt plus c, that's going to be, C1. That's going to give me e to the C1 times e to the kt. And what I'm going to do here is this is going to be t of t is equal to 70 plus, and this right here, we'll say C2 is equal to e to the C1, C2 e to the kt. All right. Now, notice up there it told us that t of 0 is equal to 300. Okay, when the cake came out of the oven, it was 300 degrees. And so we can use that to find C2. So we've got t of 0 is equal to 70 plus C2 e to the 0, and that is equal to 300, which that tells me that I've got C2 is equal to 230. See, that goes to 1, then move the 70 over. So I've got t of t is equal to 70 plus 230 e to the kt. Right? All right. So we've got that. So the thing that we have to find is what? Well, we want to know how long will it take for the cake to cool off to a room temperature of 100 degrees. Okay, how long will it take to get to 100 degrees? So in order to do that, we're going to need to know what K is. Well, is there a way that we can find that? Well, it tells us, where is it? After 3 minutes, its temperature is 200 degrees Fahrenheit. So what that's telling us is if we plug 3 in for T, that should equal 200. All right, so let me come up here and do that. I'm going to erase some of this. So T of 3 is equal to 70 plus 230 e to the 3K. So we're plugging 3 in for little t here. And that should equal 200. So I've got this equation here I can solve. So that's going to give me e to the 3K is equal to, let's see here, e to the 3K, that's going to be what? 13 over 23. That's going to be 130. Divide by 230. 130 over 230 is 13 over 23. And so we're going to take the natural log of both sides equals natural log of 13 over 23. And so 3K is natural log of 13 over 23. We're going to divide both sides by 3. So that's going to give me K is equal to negative 0.19018. So I've got T of T is equal to 70 plus 230 e to the negative 0.19018t. All right, so I figured out what K is. And so what do I want to know? I want to know, when does this temperature here reach 100 degrees? Is it 100? Make sure. Yeah, 100 degrees. So I want to know, when does 70 plus 230 e to the negative 0.19018t equal 100? Okay, so that's going to give me e to the negative 0.19018 t is equal to, what is that, 3 over 23. And then when I take the natural log of both sides, I'm going to get t is equal to the natural log of 3 over 23 divided by negative 0.19018. Okay, taking the natural log of both sides. See, that's just going to leave us with the exponent over here. And so this is going to be, what, 10.7 minutes is what it comes out to be. Okay. All right, so we're doing good so far. I've been leaving out a few things, but it's just some basic things. I mean, if you think, just think about it this. Solving this thing here, or where is it? Right here. Solving this thing here for t is the same thing as we did when we solved, where is it? Well, we did it somewhere. Oh, as when we solved that for k. Same thing. Okay. All right, so let's look at this. The mixing of two fluids sometimes gives rise to a linear first order differential equation. dA dt is input rate of salt minus output rate of salt. So that's Rn minus R out. All right. So, and it's dA dt is equal to that. The input rate minus the output rate. So let's look at this. It says a large cylindrical tank has 300 gallons of water in which 50 pounds of salt is dissolved. A mixture with 2 pounds of salt per gallon is entering the tank at a rate of 3 gallons per minute. At the same time, liquid is leaving the tank at a rate of 3 gallons per minute. So it's entering the tank and leaving the tank at the same time. Find the equation for the amount of salt in the tank at time t. All right, so we've got the rate n. So that's going to be, that's what, we've got 2 pounds of salt per gallon. So 2 pounds per gallon times the rate it's entering, 3 gallons per minute. 3 gallons per minute. And the gallons cancel, and we're left with 6 pounds per minute. Okay, that's the input rate of salt. Now let's look at the output rate of salt. All right, so at the same time, liquid is leaving the tank at a rate of 3 gallons per minute. All right, so we've got 3 gallons per minute. Okay, that's the rate it's leaving the tank. Now, what do we know? Amount of salt in the tank at any time t. Okay, so that's going to be the amount of salt divided by the number of gallons in the tank, which is 300. Whoops. Yep, it's going to be A of 300, and that's pounds per gallon. All right. So because A is the amount of salt at any given time. Okay. And then, so we got A pounds per the number of gallons, we got 300. And so we can see gallons cancel out there. We get 1 over 100, and that's going to be pounds per minute. So our differential equation, we've got dA dt is equal to the rate n. Oops, that should be A over 100, which is 1 over 100 A. All right, so now And then we also know that A of 0 is equal to 50, right? Says a large cylindrical tank has 300 gallons of water in which 50 pounds of salt is dissolved. Okay, so we know 50 pounds is the initial. And so we have a differential equation here, dA dt plus 1 over 100A equals 6. So we're going to do integrating factor here. And so our integrating factor is e to the integral 1 over 100 dt, which is equal to e to the 1 over 100 t. Okay, and so we're going to multiply each term times e to the 1 over 100 t. And so remember, the left hand side becomes the derivative of the integrating factor times a, and that's going to be equals 6 times e to the 1 over 100 t. All right, so what do we do now? We have to integrate. So we're going to get e to the 1 over 100 t. A is equal to, that's going to be what, 600 e to the 1 over 100 t plus c. All right. So hopefully you see how we get that. Remember, if you have an integral e to the, I don't know, let's just call it ct, I guess, dt. Okay, just forget about the problem we're working on now. If you're integrating and you have a constant there, okay, let's make that constant a, so you don't, because that c is not the same as this c here or any of the k's. Let's just say we have a constant a. If we integrate that, we get 1 over a e to the at, okay, plus c. That's the integral of that. So if we integrate this, that's going to be what? 1 over 100 is 100, so 100 times the 6 is 600. And if you don't see that, you can go back and you can use basic use substitution here to integrate that. You can let u equal 1 over 100 t, so du would be 1 over 100 dt. You can go and do that, but I'm not going to show that. If you're in this class, you should know how to do that. So we're going to get a is equal to 600 plus c e to the 1 over 100 t. Oops, negative 1 over 100 t. We just divided both sides by e raised to the 1 over 100 t. And then we have a of 0 is equal to 600 plus c e to the negative, well, we're plugging 0 in for t, so that would be raised to the 0, and that is equal to 50. Remember, we got that earlier. And so this right here tells me that c is equal to 550. Right, if we solve this equation here for c, so I get a of t is equal to 600 plus 550 e to the negative 1 over 100 t. Let me write that 100 better. All right, and there's your answer. And oops, is equal to negative 550. Boy, I'm missing all kinds of signs in this video. All right, so there you have it. And then you can determine how much. Is it anytime, you know? This is in what, minutes? We're in minutes. So, you know, if you want to know after 10 minutes, plug in t. Okay. All right, let's look at another one. It says a large cylindrical tank has 300 gallons of water in which 50 pounds of salt is dissolved. A mixture with 2 pounds of salt per gallon is entering the tank at a rate of 3 gallons per minute. Sounds just like the other problem that we worked. At the same time, liquid is leaving the tank. Here we go, at a rate of 2 gallons per minute. So notice the rate that it's entering and the rate that it's leaving are different this time. In the previous problem, they were the same. Find an equation for the amount of salt in the tank at time t. All right, so we know we've got dA dt equals Rn minus R out, right? And remember, A is amount of salt. Okay. All right, so we've got our amount in. Well, that's going to be just like last time. We got 3 gallons per minute times 2 pounds per gallon. And that's going to be 6 pounds per minute. Okay, the gallons cancel. Now let's look at the R out. So that's going to be 2 gallons per minute. All right, at 2 gallons per all right, times, okay, so times the amount of salt. So the amount of salt is A, okay, is your amount of salt, over, now, how much liquid will be in the tank? Okay, so notice last time we said we divided by 300. That's how much liquid's in the tank, because it was entering and leaving the tank at the same rate. So it was just that 300. Okay. All right. Didn't change. But this one is let's write it down like this. After t minutes, okay, we've got, well, let's see how we want to do it. We've got, after t minutes, we have 3 gallons per minute minus 2 gallons per minute, right? It's coming in at 3 gallons per minute, leaving at 2 gallons per minute, which is 1. Well, I wouldn't say that's after. That's not really after t minutes, but we have 1 gallon per minute. And so now we can say after t minutes, there's going to be, that's going to be 1 gallon per minute, okay, times t minutes, times the number of minutes you go, all right? So every minute there's 1 gallon. So after 3 minutes, it would be 3 gallons. 4 minutes would be 4 gallons. And so that is going to equal what? That's going to equal t gallons. See, the minutes will cancel. I'm left with t gallons. So the amount of liquid in the tank is going to be the 300 plus t. Oops. And that's pounds per gallon. And so the gallons cancel, and so that's going to be 2A over 300 plus t pounds per minute. So our differential equation dA dt is the amount in minus the rate out. Where is it? That's going to be 2A over 300 plus t. All right, and so we have a differential equation, dA dt plus 2a over 300 plus t a equals, whoops, already got the a up there. I like separating. I like separating the a. Oops. Well, is it going to erase? There we go, equals 6. All right, so now we need to go ahead and solve this thing. So we can do integrating factor. That is going to be e to the 2 times integral 2 times 1 over 300 plus t dt, which is e times 2 natural log of 300 plus t, which is e natural log 300 plus t squared, which is just 300 plus t, and then all of that squared. And that would be our integrating factor. So what do we do now? Well, we have to multiply both sides of this by our integrating factor. Okay, and once again, remember, when you multiply the left-hand side by the integrating factor, that's going to be d dt times the derivative of the product of the integrating factor times a. And that's going to be 6 times 300 plus t squared. And so if we integrate both sides, well, this is going to be, well, let's write it all out. d dt, and that's going to be 300 plus t squared a dt equals 6 integral 300 plus t squared dt. Oh, I'm running out of room. How about that? We may have to go back and erase some of this stuff. All right, so we're going to get 300 plus t squared a is equal to, now just think of this, I mean, what are we going to get here? 2 times 300 plus t cubed, right, plus c. And so, I mean, basic U substitution there. You can do that. I have confidence in everybody that they can do that. So we have a of t is equal to 2 plus c times 300. Oh, wait a minute. No. We've got 2 times 300 plus t plus c times 300 plus t to the, not squared, but to the negative 2. All right. So now we can solve for c, okay? And now I'm going to have to come up here and erase this because I ran out of room. I didn't leave myself enough room. And by the way, we don't want to do that. Let's write this as, that's to the negative 2. Yep. I'm sitting there erasing all that stuff down there. We don't want to do that. All right, so remember, we have our initial condition. Where is it? A large cylindrical tank has 3 gallons of water in which 50 pounds of salt is dissolved. So that tells us that a of 0 is equal to 50. So I'm going to solve for c. So a of 0 is equal to, that's going to be 2 times 300 plus 0 plus c times 300 plus 0 to the negative 2 should equal 50. And look, when you go and solve this, you're solving this equation right here for c. And I have confidence that you can do that. And that shouldn't be too hard. You're going to get c is equal to 495. 1, 2, 3, 4, 5. And so we have A of t is equal to 2 times 300 plus t plus 495, 1, 2, 3, 4, 5 times 300 plus t to the negative 2. And so there's your differential equation. And then you can figure out how much is in there by just plugging in different values for t. Okay. All right, well, we got one more example. All right, so we've got series circuits. For a series circuit containing only a resistor and an inductor, Kirchhoff's second law states that the sum of the voltage, this is sum, I know that's hard to see, sum of the voltage drop across the inductor L times di dt and the voltage drop across the resistor IR is the same as the impressed voltage E of t on the circuit. Thus, we obtain the linear differential equation for the current I of t. It's right here, where L and R are known as the inductance and resistance, respectively. The current I of t is also called the response of the system. Okay, so that's I of t. It's kind of like your Y there. The voltage drop across a capacitor with capacitance C is given by Q of t over C, where Q is the charge on the capacitor. Hence, for the series circuit shown in the figure, Kirchhoff's second law gives Ri plus 1 over Cq is equal to E of t. But current I and charge Q are related by I. Okay, so the current I, if you take the derivative of that, that's going to give you the charge Q. Okay, so the above equation becomes the linear differential equation R dq dt plus 1 over Cq equals E of t. All right, so let's look at an example here and see what they give us here. It says a 12-volt battery is connected to a series circuit in which the inductance is a half Henry and the resistance is 10 ohms. Determine the current I if the initial current is 0. All right, so right off the bat, we know that we're going to use L is equal to, L times di dt plus Ri is equal to E of t. So I'm going to use this one. Notice in this one they give me the inductance and the resistance. That's all they give me. So I've got let's see, where is it? Yeah, where I've got L the inductance and R the resistance. That's what they give me. I'm going to use that equation. All right, so here I've got L is 1/2, R is 10, and I've got E of t. We've got a 12-volt battery. That's 12. All right, so I've got 1/2 di dt plus 10I is equal to 12. So obviously to solve this, I need to multiply everything by 2. So di dt plus 20I equals 24. And you can see here we have a basic equation to solve, integrating factor, and also I know that I of 0 is 0. Determine the current I if the initial current is 0. So at time t equals 0, the initial current was 0. All right, so, we'll go through this kind of quick. E to the integral 20 dt which is e to the 20t. Multiply both sides by e to the 20t. So we know over here that's d dt times e to the 20t times I equals 24 e to the 20t, right? All right, so now we're going to integrate both sides. That's going to give me e to the 20t I is equal to, that's going to be what, 24 over 20 out in front. So that's what, 1.2 e to the 20t plus c. All right, so I get I is equal to 1.2 plus c e to the negative 22. All right, and so we know I of 0 is 1.2 plus c e to the 0, and that is equal to 0. So this tells me c is equal to negative 1.2. So I get I of t is equal to 1.2 minus 1.2 e to the negative 20t. All right. So before we leave out of the video, let's go ahead and just let's write this down. Let me give you some extra stuff here. And this is not part of working this problem, but this is some knowledge and terminology you may need to know. When e of t is equal to e naught is a constant. Okay? So when e of t is a constant, we'll get I of t is equal to e naught over r plus ce to the negative r over l t. And as t goes to infinity, the second term approaches 0, right? If we take the limit as t goes to infinity, this term here is going to go to 0. And hopefully everybody can see that. Such a term is usually called a transient term. Any remaining terms are called the steady state. Part of the solution. In this case, e naught over r is also called the steady state current. For large values of time, it appears, so this is when t gets big, that the current in the circuit is simply governed by Ohm's law, E equals I R. Okay, So that's just give you a little bit of terminology and stuff, and so you could see some of this stuff. Okay, transient term, steady state current, steady state part of the solution. Okay. All right, so I hope you enjoyed that video. I hope it helped. Check out my other videos. Give me a like, share, subscribe, comment, and I'll see y'all in the next one. Later.